vehicle. And the vehicles have run well through 3 winters, down to minus 20 degrees C. That's something that some technologies can't claim. These technologies of the fuel cell are allowing us to do things that don't compromise what the customer expects, which is running in hot, running in cold. They want the car to perform for them. We've also deployed into fleets. The post office and the military have used these vehicles as their own work vehicles. So you can think about how the load cycles and duty cycles of these different cars can behave differently if you're using them to deliver mail and you're stopping often on street corners. We're learning about how that applies to the fuel cell, and it's done a very good job in these situations. And we've also, in Europe, deployed one of the fuel cell vehicles as the equivalent of AAA for Europe. It's out saving stranded internal combustion engine motorists. So I personally like this one. And we've deployed a fairly substantial fleet in Europe and other countries around the world because we're evaluating how the technology varies with the way it's being used in different parts of the world. And what we're learning is it's universally meeting customer expectations, depending upon, or independent of which country we've deployed the vehicles to. And we've fueled a lot of hydrogen. We have some stations that we know have fueled more hydrogen than any station in the world. And we have 16,000 refueling events that have happened on the Equinox fleet and 36,000 kilograms of hydrogen. Just to put that in perspective, 1 kilogram of hydrogen is about the energy of 1 gallon of gasoline. So that's like 36,000 gallons of gasoline. And then there's the community outreach. It is important to educate. And I really like this picture here on the left because I can't think of a vehicle I can take to a school and ask the kids to get down on their bellies and smell the tailpipe and not feel bad about that. This is clean because all we do is make water. And we've had the unintended real-world experience as well. I think we have the honor, maybe, I don't know, of saying that we've had the first hydrogen-to-hydrogen fuel cell vehicle collision, and we've also had the first gasoline-to-hydrogen fuel cell collision. So now that fleet of 119 is 118. But the important thing is that it's been safe. We have not lost any hydrogen in any of these collisions because these are some of the most tested vehicles that we've ever done. And we've proven that the hydrogen technology can be safe. And when you couple it with technology like OnStar, where we can immediately communicate when the vehicle is involved in an event, the first responders can get there quickly, and we've trained them on how to deal with hydrogen. And so that fleet continues to run. We have over 1.2 million miles right now, and Jay Leno does use it to water his plants periodically. So where do we go from here? We've had a lot of successes with it, but the next step is to move into the commercialization phase. And that unit you see on the left is the propulsion system that was in those Equinox vehicles. If I had it standing here next to me, it would be about the size of a file cabinet. Very big, very heavy. That isn't really something that you can put into a low-hood line vehicle. So the Gen 2 design that you see over on the right-hand side, that technology we're developing for a commercial-ready introduction. That would take about half of the parts out. It takes out 100 kilograms of mass. It's about half the size. So it takes the cost down as well through integration of function by parts in the powertrain. And the cost function is something we need to think about very quickly here because what we started with was a system that was about 11 times its mature cost expectations. And that's what is on the road today in those Equinox vehicles that use 80 grams of platinum, which is an expensive precious metal. But by coming through this, if you move from the right to the left on this chart, you'll see the progression in technology through design. And then if you come from the back to the front, you'll see what happens as you scale to higher and higher volume. And the solution here is to both go through learning cycles so we can bring the cost down and motivate innovation in the supply base, as well as bringing the volume up so we can get the scale economies. If you think about it, an internal combustion engine has literally been through hundreds and hundreds of learning cycles through an entire industry that's focused on that as the prime mover. So we need to push quickly to get through these first learning cycles on the fuel cell and realize some of the same benefits that have been achieved in internal combustion engine technology. By the time you get to that 1X 2022 timeframe that you see down there in the lower, or in the front and to the left, that's an important point because now we're at less than 10 grams of platinum, which is about the same precious metal loading that you have on a catalyst for an internal combustion engine. The other thing that we've been working on with significant progress has been durability. The first Equinoxes that hit the road were about at 30,000 miles of expected durability. Right now, the vehicles are capable of about 80,000 miles without major changes to any of the hardware. And that Gen 2 architecture will meet full automotive durability expectations. So you saw, Sasha showed a very nice presentation about what's happening in Germany, and that's really should be inspiring to all of us. If we do cooperate properly, we can move toward the infrastructure and the vehicle deployments that we need to make this happen. And I just wanted to emphasize here that this week, actually, Japan, they revised their own plan. And it's important to note that in their revision, they are also saying that by 2025 they will have 1,000 stations, and they're saying they will have 2 million fuel cell vehicles on the road by that point. 2 million fuel cell vehicles. That's a lot of vehicles. And that means, again, it's a coordinated government industry effort to make that happen. And if you do that, you can easily take from these two templates that have been set up in Japan and in Germany and apply that same model to individual states within the United States. So Germany, which might be neighbored by other countries that might not have at that time an infrastructure, really faces the same challenges that states like California, Connecticut, New York all have, and they are looking at their own infrastructure investments. And then Hawaii is very similar to the situation in Japan, because like Japan, you don't have to worry about people driving the vehicles out of the state. They'll hit a beach very quickly. So the way we're looking at it for North America and the United States to introduce these fuel cell technologies and the station deployments is very much the same as what you saw for the German model. Start with the population centers, large metropolitan areas, and it doesn't take a big investment. It's about 30 to 50 stations depending upon how big the metropolitan area is. And here you can see in the example of Southern California around Los Angeles, 30 to 40 stations spaced 3.6 miles apart can satisfy a market that's basically has 15 million drivers in it. And if you connect through the major destination corridors with another 10 stations, they can drive to the places that they typically take their vehicle, Las Vegas, Palm Springs. So that's an important thing to think about as we look toward the United States and how you can deploy infrastructures into this country. And then the other thing I want to point out is one of the big advantages that fuel cells hydrogen offers is that you can have the no compromises solution to the customer. You can have the quick 3-minute refilling times that can allow you to get 300 miles of range. But it means that we have to coordinate and we have to use the state-of-the-art technology, which is 700 bar technology with communication during the refill events, as well as a minus 40 degrees C chilling in the pump. That lets you put enough hydrogen on board to meet all of those targets that I've just gone through and explained to you. So I'd like to end with these key points. What we're seeing now is that in order to meet the petroleum reduction and greenhouse gas emission reduction targets that the United States has set, the only way to get there is to include fuel cell technology, specifically hydrogen fuel cell technology for personal mobility. We also know that the technology is commercial ready now. It's already demonstrating its capabilities. The next step is to move through these first learning cycles as rapidly as possible, scale the volume, and then realize the real cost potential of the technology. And Germany and Japan aren't waiting. They're moving forward. They're doing this. The United States will be left behind if we don't start this process now. It's not an easy thing to jump from one energy economy to another. As I showed you, it takes dedication to a consistent vision. It means consistent policy as we move forward. So that is a critical thing that we've got to keep in mind. And then the Department of Energy initiatives that really helped kickstart a lot of these technologies need to be supported, and we need to expand upon that. We can't end with just showing in a demonstration that these technologies are good and capable. We've got to push through those first couple learning cycles when it's a very perilous point that you don't want to slip backward. You've got to keep the station infrastructure supported with enough vehicles, and you've got to get enough vehicles growing out there with an infrastructure that doesn't compromise customer expectations. And that means, in the end, that some sorts of incentives need to be put in place because the technology will be more costly when it first comes to the market. So that's my presentation. Thank you.